everyone. Welcome. It's very nice to be able to share my research a little bit more. I wanted to start off by giving a little bit of background about ecological footprint and biocapacity, since my thesis is mostly focused on biocapacity, just to get a little bit of a recap on what it really entails. So, ecological footprint and biocapacity are sister metrics, which are reported in the same unit, global hectares, which are hectares of globally average production. The ecological footprint of consumption is built up out of 6 categories, land categories, that correspond then on the right to the biocapacity components. And everything that goes into the ecological footprint is everything that we consume. So your electronics, your stuff for your house, food, transportation, and your waste as well. And then on the biocapacity side, we have the natural ecosystems that support that consumption and also support taking up the wastes from that consumption. And these two can be balanced against each other. What happens then, for example, if ecological footprint is higher than consumption, we're in overshoot, or if biocapacity is larger than ecological footprint of consumption, you have more ecological space in your specific area. And the National Ecological Footprint and Biocapacity accounts, I'll just say NFBA from now on because it's too long, are the accounts where we make that balance for all the countries for every year, and we update that every year as well. So then my thesis research focused on the built-up component of biocapacity. Now I wanted to show this little framework of how those biocapacity calculations really work. So on the left, you have the area. They're hectares of 5 different land use categories or land cover categories, depending on the category, which then get multiplied by first a yield factor. The yield factor says something about the yield from a hectare of, let's say, forest in country A compared to the world average. So we know all the hectares of forest in the world. We know how many forest products are yielded from all those hectares in the world. We know the number of forest hectares in country A. We know what the forest yields in country A, and then we can see how big is that yield compared to the world average. So that's the yield factor. And then we have the equivalence factor, which talks a bit more about how productive is a forest compared to a cropland, compared to a grazing land. And as you might have already noticed here, is that the built-up land is using cropland yield factors and equivalence factors in our framework. And that's related to the history, to the historical idea that we started cities or built up areas in places where there was high agricultural productivity. So any land that was being built there was taking up the space of cropland. And from that same logic, we have said that the built up biocapacity of an area that is built up will be the same as its ecological footprint. So they cancel out against each other. This means any changes in built up land in the country don't have any impact on the ecological balance because the balance is always equal. Still, it's very important for us that we accurately describe those built-up areas. Built-up areas are super important. Most people live there. 65% of people are expected to live in built-up areas in 2030. And these areas are very important, for that reason. Also, a lot of production and economic activity happens there. There are also areas where a lot of people are vulnerable to heat waves, floods, stuff like that. And we have vegetation in our built-up areas that is still giving us ecosystem services, that is still cooling our air, taking up pollutants, stuff like that. So it's really important that we get a more accurate assessment of those services. And then we all would like to think with more awareness coming into how important green areas are in cities. Not everywhere sees trends of urban greening. A lot of places in the world where the highest urbanization is happening, the highest rate of urbanization, are actually urban browning trends. So they're becoming less green. It's important for us that we show those trends in our data as well as we go into the future. Yeah. And as you can see on this image here, it's about the Sustainable Development Goals. Sustainable Development Goal number 11 is about sustainable cities. And you can see that no country in the world has reached the SDG goals that are connected to that SDG. And those are supposed to be reached in 2030. So it's not looking too good in that aspect. It's very important to research this. So I picked a study area in a coastal city in the Netherlands, The Hague, which is the administrative capital. The city was chosen for a couple of reasons. First and foremost, because I know the city very well. I'm there right now, so it's very good to be able to fact check. Well, we'll get into it later, but fact check my training data. Also, the city is coastal, so you have different types of soils going from sandland near the ocean to peatlands inland, and different types of vegetation that are growing on them. A little bit about the city is that it has a nice coastal climate, of course, very nice. And within the city limits, we picked a polygon, a square that had the 2,800 hectares, which is a good cross-section of the city. It has industrial areas, new built areas, older areas, parks, dune lands, which were very important, and of course, water features. So all these different land cover types could be included in the study. In the research method, because I was developing a method, I had to test multiple different, you can make many choices when developing a method. And I had to look into each choice and see what impacts each choice have on the final result to then say, maybe in the future, which one is the one you should use. So I had two data sources. Pleiades Neo is a multispectral satellite from Airbus. It's a commercial satellite, so the images are not free. And Sentinel-2 is a satellite from the European Space Agency. They are free, also multispectral. You can see here the main difference between the two is the resolution. So Pleiades Neo has a 1.2 meter resolution, whereas Sentinel-2 has a 10 meter resolution. And in many studies in the past have said that 10 meter resolutions is too coarse for urban applications, but for our application being a little bit different from those applications, we still use it as the comparison. And in these satellites, there were 4 main wavelengths that I used to do the analysis. So they were the blue, green, and red visible light, and the near infrared. And the near infrared is really important because it helps us distinguish vegetation. So if you're looking, for example, at an artificial grass field from the sky, from space, it's green. It looks green, it's green. You could not distinguish it between an artificial grass field and a regular grass field. But the near infrared has very different signature for vegetation compared to non-vegetated areas. So we can use that to make sure we don't identify things that just happen to be green as vegetation. And then vegetation indices are indices that are a combination of different bands, usually red and near infrared, to highlight specific properties of plants. It's very interesting. Very smart people made those indices. So that's the first step. And then for each data source, I made training data and validation data. And they were different between the sources because Sentinel-2 and Pleiades Neo had slightly different identifiable classes of vegetation cover or land cover in general. And of course, we're just very different in how you can create the polygons for the training and validation data because they need to be pure. You're not supposed to use pixels, for example, here that are a little bit of green and a little bit of gray. You should use the pure pixels for your training and validation data. Then the second comparison of method was between segmentation methods. So there's two main segmentation methods. There's pixel-based and object-based. Pixel-based, you use the image as it is, and you use the algorithm on it as it is, and you just go. Object-based first has a step where it groups pixels together. You have a lot of different characteristics that you can filter out, different sliders in the program that I used where you can tweak it to get the right segmentation. And it's often used, for example, to get rid of shadows, which will be important later. And then I had algorithms. There were 3 algorithms tested for each segmentation method for each data source. So in total, there were 12 final results. And then the second part of the thesis was the literature review, which focused very much on how does the vegetation that is identified inside of a city relate to the vegetation that we use, that we find in our national accounts. How does a tree that is in a city compare to a tree that we have in a forest? How do they compare? How does their production compare? And yeah, that was actually it. Yeah, next slide. So these are the first results, well, the final results for Pleiades Neo. You can see each result as it is. They are lettered. They have a K value in the bottom left corner of each frame. That's an accuracy assessment. So it is checking whether a validation polygon that I have made is actually identified by the algorithm as what that validation polygon is supposed to be. And that's how you get the accuracy. It's supposed, if it's fully accurate, if it's perfect, then it's 1. Acceptable results start from 0.8. So you can see some of them are not as accurate, but still actually quite good values. And then on the bottom right corner is the global hectares that this study area has in bioproductivity. So I wanted to highlight here the middle column of results. First going to the top one, because one of the issues I was facing for a long time were misclassifications of shaded areas being identified as dune sands. So in the left here, that's where the actual dune sands are. But all these yellow blobs that are here, all these lines, they are misidentified. There is no sand there. They are shadows from buildings, cast by buildings, on some other land cover type, which I can't identify, being identified as dune sands. So it turns out that the signature for these shaded areas was very close to the signature of the dune sands, and therefore there were a lot of misclassifications. The interesting part, of course, is that this has a very high accuracy score. And this is mainly also because the validation polygons that are used to get this score are needing to be placed in areas where the blob is homogeneous. And these areas where the misclassifications are happening are not homogeneous enough to put a validation polygon. So that's one of the issues that comes with this type of validation, is that you can't validate the parts that have the highest chance of error, which is definitely not great. But visually, we can, of course, still say it's not great. Then compared to the object, so the segmented image, you can see a lot less dune sands are identified all around the city. Still correctly identified here in the corner, but seemingly from this, the segmentation, so the grouping together of the polygons, has filtered out some of the shaded areas, grouped it together with just the normal pavement or the normal buildings, and just created a more smooth image. What I do see here is that a lot of places where there should be water, here and here, there's a canal, which goes all the way here, over and up, they are being identified, and here as well, as being dune sands when in reality they are water. So that's one of the reasons why this K-score is a little bit lower, because the water areas were big enough to have validation polygons, and seemingly it's not quite right. Next is the Sentinel data. And one very important thing to note here is that there's an extra class. So these images have an extra class here that's called urban tree canopy. This class was born out of a lot of the 10 by 10 meter pixels in the very urbanized area of the study area, included both hard infrastructure, roads, buildings, whatever, but also trees that were above it. At least here in the city, trees aren't usually 10 by 10 meters. So there were a lot of pixels that had a tree in it, some road in it. What are you going to do with that? If I just had only forest as a class and infrastructure as a class, it would be identified maybe as shrubland or as only infrastructure, when there's definitely green there, vegetation there. So I started to make training polygons for these specifically mixed pixels. That's something you're not supposed to do, but in this case, because it's its own class that is mixed, it worked really well. So you can see here, for example, this is an actual forest inside of the city, and here as well. And they are correctly identified as forest, not as urban tree canopy. And all of these trees that are in the city are correctly identified as urban tree canopy and not as forest. So I was really happy with this. And what I was able to do with this was also give the urban tree canopy an adjusted value for how productive they are, because trees that are on their own, that are along trees that don't have a lot of space for their roots, they don't produce as much from the literature review. Overall, we get this beautiful graph, which has all of those runs, those results you just saw, with their global hectare result for the study area. And here in the middle, you have the value that the study area has when using the NFBA 2025 values for built-up area, the cropland values. And you can see, well, there's quite some variation within the results that I got. They're very close to each other compared to the outlier, that is what the NFBA 2025 is over here. So, of course, I compared a lot of different choices within the method. So the resolution, so Pleiades versus Sentinel, only explains 3.5% of the variation in global hectares. So it's not actually that important, turns out, for this specific analysis. Whether you use the very high resolution image or the medium, it's still actually high, but the 10-meter resolution. Then in segmentation, this is where the biggest difference in the results is coming from. So, well, specifically for Sentinel, the variation can be explained by segmentation for 27.3%. Very, very significant. And one of the reasons that this could be is that because the pixels are already bigger, they already, in a way, segment themselves, already filter out some of those shadow issues that was mostly an issue in the Pleiades images. And then the segmentation is not very necessary anymore on top of already that lower resolution. For Pleiades, also segmentation was a big factor, but not as big as in Sentinel. And then the different algorithms, depending on the algorithm, the differences were 3% or 12% or anywhere in between. So the algorithm with the biggest difference in results, I'm quite sure, is random trees, RT. They had the biggest differences between them. And the smallest one, I'm not entirely sure anymore, because this is a while ago that I wrote the thesis. but I know which one had the biggest one. So because we know that changes in the built-up component do not change ecological balance, the results on the ecological footprint per capita and biocapacity per capita are the way that we can see the biggest, well, the only change. So in the current NFBA 2025, the ecological footprint per capita in the Netherlands was 2.99 global hectares. If you change out the built-up component from that for these values, so assume that the results from my study are correct and apply them to the whole of the Netherlands built-up areas and are representative for all the Dutch built-up areas, then you get 2.9 global hectares per capita to 2.92. So it's definitely a bit lower than the ecological footprint per capita was, but it doesn't actually amount to a change in the ranking of the Netherlands among similar countries or any countries for that matter if you list everyone out. And for biocapacity, the change, of course, is the same amount of global hectares, but the biocapacity per capita is much lower than the ecological footprint per capita. So it went from 0.9 to 0.82 to 0.83 global hectares per person. So it's a good amount of change. It's actually less change than I expected it would be, since the Netherlands is quite an urbanized and built-up country as it is. So I expected the results would be more significant. They are significant, but I expected it to be more. But it's interesting to see. So yeah, that's it from me for now. I'm open to questions. I just wanted to thank my supervisors again, Eric and Inga. And I just wanted to also say you can always reach out to me via email if you have any more questions. And the thesis is also published on the Icelandic open access website Skemman. Thank you.